Okay, so I accidentally hit stop there, but I meant to hit pause. It's okay, because this is about as far as I think we've all gotten in terms of catching up to the week 5 homework. So let's dig back in. I'm going to find the right spot on Fraser Solutions. Yeah, okay, so here's Fraser's solution for that same problem, and it looks almost exactly like Sean's, so nice job. There it is in all its glory. Um, got the sum, the average, standard deviation, and the max k-var h sum. And guys, just to reiterate what that k-var h is, so if you've taken 213, I'm assuming you have, by now you know that there's a little power triangle. In fact, I can bring that up. I've got a neat little document I've done on that. This is one kind of fun way to think about it. So this bottom line here is what's called your true power. This thing along the hypotenuse is the apparent power, and this is called the reactive power on this vertical axis. I'm going to show you one more way to look at it. Well, in terms of a farmer plowing a field, the stuff on the bottom is the work done. It's the actual stuff to separate the dirt. The stuff on the top here is sort of this guy bouncing back and forth, and it's just, the farmer himself is getting tired, but he hasn't really put any of that energy into plowing the dirt. And the rest of it is just kind of the up and down that's just annoying to the horses. So anything that's not on this bottom line, like literally the bottom line, is just wearing down the farmer, wearing down the horses, and not doing anybody any good. So that's why you want this true power only along the bottom. And that's what you get from a purely resistive load versus a inductive, which is L, or a capacitive, which is C. The mechanical analogy for induction is mass, and the mechanical analog for capacitance is K for spring. Hooke's law. Here's another neat little online resource that I found. So true power is what we're after. That's just IR squared, so current times resistance squared. E in this case is voltage. Reactive power is listed as Q, which is I times X, which is the reactance. And apparent power is I squared times Z, which is the impedance. And the impedance is what we're familiar with when you get that inductor or capacitor in the series. Okay. So if you have a pure resistive circuit, there's no reactance at all. You've got zero VAR, zero reactance. You do have an apparent power of 240, but that's fine. It's equal to your true power. In this case, if you have an inductor, you end up with a little bit of Q, and the reactive power is actually, well, this is if you don't have any resistance at all, the reactive power is the same as the apparent power, and there's no true power. You're just sort of sloshing electrons back and forth. If you've got a resistor and an inductor, it's a little bit different. The apparent power will always be greater than or equal to the true power, in this case 169. And here again is that power triangle, and it's just the Pythagorean theorem. So the apparent power, which is volts times amps, is its square is the sum of the true power, which is squared, and the reactive power, which is squared. That's pretty much it. Pretty simple. Yeah, okay. So that's what you're being charged for, is that kVAR, that reactive. The R just stands for reactive. So guys, all I'm doing right now is I'm just getting into this interactive session. This is Blackboard Collaborate. I'm going to see if anybody's in the session here. I'm going to click on the meeting. Starting up. Please run it. Don't need to run it twice. Oops, maybe I'm only running it once. Come on. Once you start running it, you'll see the application at the bottom. Okay, there we go. There's the little arrows. Nice. Loading. Third millennium education. I'm not sure I want the double arrow, but okay. Okay. I'm going to connect. Wireless. Okay. I don't need to record. Well, anyway, I am the only person in the room. So lonely, but we can try again. Let's try again next week. I'll be on Pacific time, but we'll schedule something. So anyway, I'm going to minimize that and get back to where I was. Hope you guys can join me next week. Okay, not a problem. Still recording. Okay. So let's get into some of these other spreadsheets. So I think we're all set for this problem. We're in week 5. We did the Seattle light power factor calculation. And I'm going to pause again. Okay, I'm picking up here in problem set 5 again. So let's see where we are with this one. Okay, it looks like, yeah, Chris did a really good job. Oh, a couple guys, I think there was an error here in just the kVAR cost. That was all. Problem 2. This is close, but not quite, Chris. That's looking pretty good. There were a couple subtleties though in the kVAR cost. Problem 3. This is also pretty close too, but just not really close. So let me just pause here. Take a look at another one. Save that. So we're like right in the middle of grading everybody. It looks like everyone's giving it a pretty good shot, but let's look and see what Fraser came up with. That second problem in problem set 5. Okay, so getting back into Burbank. So this is problem 2, Burbank. A couple different ways to do it. Here are the kilowatt meter data. Peak power factor. The kVA definition is just the power divided by the power factor. And then the monthly cost, let's look where that comes from. So again, we're looking at a and an if statement. Let's make that just a little bit bigger. So we can inspect it right here. So if C16, so that's the kVA definition, so it's the kVA charge, times B10, so B10 is the kVA rate, so that's dollars per kVA month, is greater than B11. There's the minimum charge. Then what we're going to be charged is C16, which is again how much kVA we used, times B10, which is the rate. Otherwise, just use the minimum. So in this case, the minimum was never actually triggered. So we always paid the flat rate. Yep, we always paid the flat rate there. So there's the sum, there's the average, there's the standard deviation. Pretty simple. There's the minimum and there's the maximum for each month. Okay, pretty simple. So there's Burbank. Yep. Okay. Problem 3. Calculate the total annual operating cost for compressors in week 4. So just put them in a new tab, use the Burbank Energy and Water, the reactive charges, same. So now we're looking at the reactive rather than the apparent. Assume the same operational attributes as the week 4, problem total operating cost for the 2 compressors. Okay, so let's look at that guy. Burbank 2. So here's K var. Just calculating K var now, which is the sine of the arc cosine. I think some of you used trig or the tan before, which is also fine. Here is everything from the 100 horsepower motor. So we're looking at kilowatts used, kVAR, kVA, and power factor for each one. 15-minute average. There's where this is coming from. 15-minute average. Just kind of scrolling right down through these. Oops. And the same thing is done for the kVAR. So we can do it for the 100 horsepower motor. We can do it for the 150 horsepower motor. Again, these are kind of running averages. Yep. Yep. The use factor is the same. Energy cost is the same. This is your demand cost. There's your kVAR cost. And there's your basic fee cost. And so the demand is the maximum of the 15-minute averages. So you can see that each one of these is a minute-by-minute charge. The energy is straightforward, just averaging them times the total hours per year. Okay, and then back here to problem 2. Okay, so I'm looking back here at Fraser's solution for problem 3, week 5. So I've just got this problem 3 solution tab opened here. Average of all data. So that's coming from the previous sheet. Same thing here for the 150. Energy per year. For the 100, energy per year for the 150. There's the demand per month. Reactive demand. In this case, again, we're just using an if statement to see which of the two is cheaper. So how do we get the total cost? Well, we've got the energy cost, which is coming out of the 100 HP. We just looked at those a second ago, both for the 100 and the 150. The demand cost, again, is coming off of the 2 spreadsheets. The reactive demand, so that's 100 HP B14. Let's look where that's coming from. B14. That's the peak, so that's B8. Scroll up here a little bit. So 28 cents per kVA. kVAR, that's the peak kVAR, 54.71. Then we annuitize it. So these are what these two motors cost. The 100 is 20 grand, the 150 is 30 grand. They do a major rebuild over 20 years versus 10. So the 150 is more expensive on an annual basis, but you're paying less in demand, you're paying less in energy, less in reactive, same in the basic. So it turns out the 150 is less expensive. Okay, so I've caught us up to week 5. I'm going to finish grading, and then I've got a couple calls to make. But guys, nice job sticking with 214. It's not an easy class. I will see you next week.